Greetings and welcome to a new video series, Trend Lines and Regression Analysis. In this video, we are now going to move to looking at predictive analytics, where we look at current data and coming up with models in order to predict what could potentially happen. Many applications of business analytics involve modeling relationships between one or more independent variables and perhaps some dependent variables. For example, marketing researcher might want to predict the intent of buying a particular car based on a survey that measured consumers' attitudes towards the brand, negative word of mouth, and as well as income level. Trend lines and regression analysis are tools for building models and predicting future results. Okay, let's first look at modeling relationships and trends in data. Understanding both the mathematics and the descriptive properties of different functional relationships is very important when we want to build predictive analytical models. Often begin by creating a chart of the data in order for us to better understand the data sets that we have. Okay, and then from here, we can then choose the appropriate type of functional relationship to incorporate into the analytical model. For cross-sectional data, we use a scatter chart. And for time series data, we use a line chart. Common types of mathematical functions used in predictive analytical models include linear, logarithmic, polynomials, second order, third order, power, as well as exponential. Linear function shows steady increase or decreases over the range of x. Logarithmic functions are used when the rate of change in a variable increases or decreases quickly and then levels out. This tends to be used in marketing models where constant percentage increases in advertising, for instance, result in constant absolute increase in sales. Polynomials function, the second order is a parabolic in nature and has only one hill or one valley, while the third order polynomials has one or two hills or valleys. The power function defines phenomena that increase at a specific rate. For example, learning curves that express improving time in performing a particular task are often modeled with a power function. Exponential functions have the property that y rises or falls at a constantly increasing rate. For example, perceived brightness of a light bulb grows at a decreasing rate as the wattage increases. When we are using exponential, the base of natural log is often used for the constant b. R squared is a measure of the fit of the line to the data. The value of R squared will be between 0 and 1. The larger the value of R squared, the better the fit, and all data points will lie on the line. Trend lines can be used to model relationships between variables and understand how the dependent variable behaves as the independent variable changes. Let's look at an example. Market research study has collected data on sales volumes for different levels of pricing for a particular product. Here we can see the graph. If you look just at the dotted lines, they show the relationship between price and sales, and they clearly appears to be linear. So a linear line was fit to the data. The resulting model of that is sales equals to 20,512 minus 9.5117 multiplied with price. The model can be used as the demand function okay, in marketing or financial analysis. Trend lines are also used extensively in modeling trends over time. That is, when the variable of x in the functional relationship represents time. Okay, so for example here, we have a chart of historical data on crude oil prices for each month from January 2006 all the way to June 2008. Using trend line, we can try to fit the various functions to this particular data. Okay, so this is the chart, okay, of the crude oil prices against time. So we can use exponential, logarithmic, polynomial, second degree, polynomial third degree, as well as third order, as well as power. So when we come out, okay, when we have modeled it based on different mathematical model, what we can find that the best fitting model is the third order polynomials. Okay, so this graph shows the fitting of the third order polynomial. And how do we know it is the best fitting? Okay, by looking at the value of r square. You see, if it's an exponential function, r square is 0.664. Logarithmic, r square is 0.382. As mentioned earlier, r square, okay, looks at the best fit to the line. It will be a value between 0 and 1, 1 being the best. Okay, 1 being exactly every single data in the plot fit into the line. Okay, so here the highest r square value is 0.928. Therefore, out of the 5 different models, polynomial third order has the best fit. Be cautious, however, be cautious when we use polynomial. Okay, the r square value will continue to increase as the order of polynomial increases. That is, fourth order polynomial will provide a better fit than a third order, and so on. Higher order polynomials will generally not be very smooth and will be difficult to interpret visually. Therefore, it is not recommended, okay, to go beyond a third order polynomial when fitting with data. Use your eye to make a good judgment.